2.11, sketch using the fewest possible calculations the graph of the following functions. And then we have 12 different functions and a hint for 8, which says that this brackets here denote the integer part of x. Okay. But we'll deal with that later on. Okay, so what I'm going to do is to go through each of these functions and try to argue or kind of think in out loud what is the kind of thinking I would do to try to sketch these figures, and then I'll show you how these functions actually look when plotted in Python. Okay, so let's start with the first one. So the first one is f of x is x plus 2 squared minus 1. Okay, so what is this going to look like? Okay, so first of all, you start, this clearly is a kind of a variation of x squared. Okay, we call this g of x squared. This is clearly a variation of that. Okay, so we know that x squared looks like this. It's a parabola. Okay, now we've seen before that if we add a number in the argument of the function, so if now g is g of x plus 2, it will be x plus 2 squared. This is similar to a horizontal shift to the left now, okay, because now the 0 of this function is going to be at minus 2, right? So when x is minus 2, g will be 0. So now this function will be like this. Okay, so like this one, but shifted to the left. Okay, and finally, if you add, let's call h of well, this f, okay. So for f of x is the same as g of x plus 2, but then subtract minus 1. Okay, so then f of x, what it will look like is just the same like this. So the 0 here will look like this. Okay, so this is minus 2, but then this is minus 1. So then this horizontal line is not 0 anymore. This is minus 1. So you will have 0 here. Okay, y equals 0. So it's a shift downwards. Okay, so this is what you will expect. Okay, this is kind of the thing you need to think about. You start with x squared, you shift it to the left, and then you shift it downwards. Okay, and so this is what it looks like. Okay, this is the original one. This is x squared, and then this is x plus 2 squared, and then minus 1. Okay, and then this point here is minus 2 and then minus 1. Okay, cool. Now for the second one, this is f of x is square root of 4 minus x. Okay, so first let's start with g of x, which is the square root of x. Okay, so what's the square root of x like? Is like this. Okay, something like that, and it's 0, it's 0. This is x, and this is g. Now you can rewrite this like this, minus x plus 4. Okay, maybe this is simpler. Okay, so if instead of writing g of x, we write h of x is square root of minus x. Okay, now the positive numbers are not in the domain, only the negative numbers will be, and this is just the same function but the other way around, right? You're just multiplying by minus x. Okay, now if you add 4 to this, so instead, so f of x is just h of x plus 4, right? Sorry, x minus 4. Do you see? Because h of x is minus and then x minus 4, which is equal to minus x plus 4. Okay, so this is just shifting this function to the right. Okay, so if we add, as before, if we add a positive number, we're shifting to the left. If we add a negative number, we're shifting to the right. And again, it's easy to see why, because the way to now this function is valued 0 is only when x is 4. Okay, when x is 4, this is minus 4 plus 4 is 0. Okay, so it would have 1, 2, 3, 4, and then the same function as before, so just like this. Okay, and this is 4. Okay, so this is what it looks like. So this is the original one. This is square root of x, and this is square root of 4 minus x. Okay, the one that we wanted. Okay. Okay. Now, so for 3, we have x squared plus 1 over x. It's 1 over x or 1 over x squared? It's 1 over x. I think I painted 1 over x squared, but it doesn't matter. Okay, so so we have two different functions, x squared, okay, and then 1 over x is this function, okay, the inverse function. So now if you sum them, okay, what you're gonna have is, let's see, so for values close to 0, this is very small, so what you have is very close to 0, you're gonna have very similar to 1 over x, and then as you get farther and farther away, this gets very small, and then this gets big, so you will have something like this. Okay, and then in the other case, we have this negative numbers, so it goes like this, and then this goes to 0, so you have something like this. Okay, so away from 0, as you go away from 0, this looks like x squared, and if you get very close to 0 in this case, this looks very close to 1 over x. Okay, so something like this. Okay, and so I realized I painted a different one. So let's what I painted was 1 over x squared. Okay, so that was a mistake. So again, this is if you just do the same thing. This is x squared. This is, and 1 over x squared is like this. Okay, this goes to infinity and this goes to infinity. So it's the same reasoning. Very close to 0, you're just similar to 1 over x, and then away from 0, you're getting similar to x squared. Okay, and so that's what it's painted here. Okay, so this is 1 over x squared. Okay, and this is the red, black one is x squared, and the blue one is x squared plus 1 over x. Okay, you see. So what you need to think about is when this function is very small, when this function is very small, and then if you sum them, you'll see. Okay, this is the kind of thinking that you need to have. Okay, 4 is f of x is 1 over 1 plus x squared. Okay, so how do we go about this? Let's see. So when x is equal to, so the denominator is never going to be 0. Okay, so this is not the same as other inverse functions or rational functions. Okay, this is always going to be positive. And so when x is 0, this is equal to 1. Okay, 1 over 1. And then for as x gets bigger, this decreases, right? So you have something like this. And then because this is an even function, as you can see, because the only term is with x is x squared, then you just have to copy this to the other side. Okay? So this is the function, kind of, and this is what it looks like. Okay. Now let's do 5. 5. It's f of x is the minimum of x and x squared. So, well, you have x is the line, okay, you know, and x squared is the parabola. We've painted this before. Okay, so what's the minimum of these functions? Okay, when x is negative, clearly the minimum of these two is x, so the minimum will be this, okay, because x is negative. And then, let's see, when x is smaller than 1, then x squared is smaller than x, okay? And so how do we know this? Well, you know, you could actually do the calculations, okay? But so if you do x squared minus x, and then so x is x minus 1 equals 0, then this is a parabola, and you know that it's negative between 0 and 1, okay? So that's just an interesting fact to remember, is that the squares are smaller than the original number between 0 and 1, okay? So this is 1, this is 1, this is the point. So between 0 and 1, the minimum is the parabola, so it's something like this. Okay? And then after that, x squared is greater than x, okay? After 1, every square is greater, so you just continue with the line, right? And so this is what it's painted here. Okay, the red one is x squared. The black one is x, and then the blue one is the minimum of the two. So then you have this, the parabola, and then it stops at 1. Okay, and then you keep with the line. Okay, let's do 6. 6 is f of x. It's the absolute value of e of x minus 1. Okay, so let's start with the original function is exponential, and the exponential goes something like this. Okay, and this is 1. Now if you have h of x, which is e of x minus 1, then this is the same thing but shifted downwards, okay, minus 1. And then so now that the crossing point with the x-axis will be at 0, okay, so if you see e to the 0 is 1 minus 1 0, okay, and then this thing is horizontal asymptote at minus 1, okay, so this is e of x minus 1. If you take the absolute value of that function h of x, what you will have is that for the positive numbers the function will be the same, but then for the negative numbers you see this thing is negative, so you just reflect it upon the x-axis, okay, something like this. Well, if I learn to paint at some point, okay, something like this. Okay, so you just copy the same curve but in a positive, okay. So this is what it's painted here. This is e to the x minus 1, and then this is the absolute value of that. Okay? Now, 7. F of x is the absolute value, the square root of the absolute value of x minus x. Okay, so let's start. G of x is absolute value of x minus x. So now we know that absolute value of x is minus x when minus x when x is smaller than 0, and then x when x is greater or equal than 0. Okay, so and then you subtract minus x to this expression, and so then you end up with minus 2x if x is smaller than 0, and then 0 if x is greater than 0. So this g of x is something like this. It's negative with a slope of 2 and then 0. Okay? So this is g of x. And then now if you take the square root of that, so the square root of g of x, what you will have is, well, the square root of this will look something like this, and then the square root of 0 is 0. Okay, so that's what the function will look like. and this is what is painted here. Okay, so the dotted line is, sorry, dashed line is square root of x, sorry, absolute value of x minus x, and this is the square root of absolute value of x minus x. Okay. Okay, this is a fun one. Okay, so we have the f of x is 1 over, and then the integral part of 1 over x. Okay, so now let's deal with the integral part. So the integral part of x is the greatest integer n such that n is smaller than x, okay, or equal to x. Okay, so if you think about the floating numbers, so you think about 2.65, for instance. Okay, so the integer part of 2.65 is 2. Okay, so you just take or 3.14, then the integer part of 3.14 is 3. Okay, not this complete bracket. But, okay, so this is the same as taking the floor function in any programming language. Okay, when you learn programming languages, you will see this floor of x. Okay, interestingly, when you have, for instance, minus 3.05, okay, the integer part of minus 3.05 is not minus 3, it's actually minus 4, okay, because this is the greatest integer such that it's smaller than x, okay, and minus 3 is not smaller than this number, it's actually greater, okay. So for the easy rule to remember this is for positive real numbers, you just take the integer part, before the dot, in a sense, or left to the dot. For negative real numbers, you take this number minus 1. Okay. Okay. So now let's deal with this. We have 1 over x, and we know 1 over x looks like this. And now, what's the integral part of 1 over x? Okay. How do we plot this? Well, the integral part, so 1 over x, so when let's say 1, 2, 3, 4, okay, and then 1/2 and 1/3, for instance. So let's see, 1 over 4, if you have any number here, 1 over 3.5, this is smaller than 1, okay, and so the floor of that is 0. Okay, so for any number that's greater than 1, the floor will be greater than 0. Okay, so you have this. And then so for numbers between 1/2 and 1, what you will have is greater than 1 but smaller than 2. So the floor of that will be 1. Okay, so this is 1 here. And then for numbers between 1/2 and 1/3, you will have numbers that are greater than 2 but smaller than 3, and so on. So you have this kind of step that goes up. And the same thing, but for negative numbers. But here, if you go from -1, for instance, -1, -2, if you have 1 over -2, you have -0.5, but so the greatest integer that's smaller than that is not 0, it's -1. So you have something like this at -1, and then the steps go again. So -2, -3, blah, 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 like that. Okay? Okay, so that's the integral part of 1 over x. How do you do 1 over the integral part of that? Okay, so 1 over this is, okay, so this is f of x. 1 over -1 is -1, so you have -1 up until -1, and then 1 over -2 is actually -1/2, so you have -1/2, -1/3, -1/4. You get closer and closer to 0, and then actually you get 0. Well, in 0 it's not defined actually, because 1 over x is not defined in 0. And then you have the same thing but going upwards, 1 over whatever n 6 and then when you get closer and closer to 1, you get to 1, and then after 1 you have 1 over 0, which is not defined. Okay, so this function is not defined after 0, so it will look something like this. But so let me plot this. The black one is 1 over x. Okay, this is what we have seen, and then the red one is the integer part of 1 over x. Okay, so this is the thing that I told you. It's 0, and then it's 1, it's 2, it's 3. So this is 1 over 2. This thing will be 1 over 3, 1 over 4, 1 over 5, and so on. Okay, and the same thing here. And then if you do the inverse of that, you have what I just told you. Okay, so this is 1 over the integer part of 1 over x. Okay, and these steps go smaller and smaller and smaller and smaller. In 0, it's not defined. Okay, not defined. And so yeah, that's it. Let's see, 9. It's the absolute value of x squared minus 1. Okay, so yeah, this is f of x. Sorry. So again, starting with x squared, we have seen if you do x squared minus 1, this is just shifting it downwards, something like this. Okay, and this is minus 1. Now you take the absolute value of this, and that means that the negative part will be reflected. Okay, so you have this thing, a parabola is going like this, and then the negative part gets reflected. Okay, so this is f of x, and this is what it looks like. So this is x squared minus 1, and the blue one is the one we want. This is the absolute value of x squared minus 1. Okay, as you can see, it's the same. It's reflected on the x-axis. Now 10 is f of x is 1 minus e to the minus x. So we know e to the x is this. Okay, e to the minus x is actually the same, but kind of reflecting the x-axis on itself over the y-axis. So you start something like this. Okay, this is e to the minus x. You can think about it as looking at the x-axis from the other side. Okay, now minus e to the minus x is the same thing, but from below. So you have this e to the minus x minus. Okay, you see, this for every value is the same, but minus, so reflected on the x-axis. So now finally f of x is this function, but shifted one value upwards. Okay, so if this is 1, then this thing, and so now this is 0 at 0, so it will look something like this. Whoa. Okay, when it should be 0 here. Okay, and so this is what it looks like. So this is e to the minus x, and this is 1 minus e to the minus x. Okay, and then 0 at 0, as I told you. F of x is the logarithm of x squared minus 1. Okay, so we know that the logarithm looks like this. Okay, it only takes values in the positive numbers, and it's 0 when x is 1. Okay, so this function will only take values whenever this thing is greater than 0, so whenever x squared is greater than 1, whenever x is not in this interval. Okay, so x has to be greater than 1 and smaller than minus 1. Okay, and it will touch the x-axis whenever this is equal to 1. Okay, so this is equal to 1 whenever x squared is equal to 2, so whenever x is plus minus square root of 2. So when you have this is 1 and this is minus 1, so for instance, this is square root of 2, and this is minus square root of 2. Okay, square root of 2 and minus square root of 2. And so this thing. So for positive numbers, this will look kind of similar to the logarithm. So something like this. And the interesting part is that this function is even. Okay, if you substitute f of minus x, substitute here, because of the square, this will look the same. So f of minus x is the same as f of x, so it's the same function but mirrored in the y-axis. Okay, so it's very different to the logarithm in that you have two curves. Okay, and so this is what it looks like. Okay, so this is the logarithm of x, and this is the logarithm of x squared minus 1. 12 is f of x is x times the sine of 1 over x. Okay, so we have seen before what the sine of 1 over x is. So the sine of 1 over x. So we know that, you know, when x goes to plus infinity, this goes to 0. The argument goes to 0, and when the sine, the argument of the sine goes to 0, the sine goes to 0. So this like this, and then because it goes to 0, when x goes to minus infinity, then the argument of the sine goes to 0, but from the negative numbers, and so this looks like that. And so this does something like this, and then when when this is let's see 1 over pi or something, this will go to 1, this would go to 1, and then just like before, you will start to have all the great numbers. Okay, so you start to have the oscillations, and then the oscillations get closer and closer and closer and closer, and then the same thing, closer and closer and closer and closer and closer. So you get a lot of oscillations here. Okay, difficult to paint. Now, if you multiply this by x, well, the first thing is that the function now becomes even. Okay, f of minus x is just minus x times the sine of minus 1 over x. But the sine of minus 1 over x is minus the sine of 1 over x, because the sine is an odd function. So this is x times the sine of 1 over x, the same as f of x. Okay, so now this function becomes even. And the interesting thing is that you get these same oscillations, okay, but then as you get closer and closer and closer and closer to 0, these oscillations become smaller because you're multiplying them by x, which is very small. So then this thing is a bit greater maybe, and then you start doing this, but then the oscillations go down and down and down, and then something like that. Okay? There's a lot of them here, and then you have to copy the same function for the other side. Okay, so now you have a symmetric function. Okay, so this is the painting here. So this is the sine of 1 over x, the black one, and then this is x times the sine of 1 over x. Okay, and you see how these oscillations go. As you get closer and closer to 1, this goes smaller. Okay, and yeah, so I made a mistake. So here, when you get away from 0, actually, so x, so the sine is bounded. Okay, it's between minus 1 and 1, and then x gets greater and greater. So what you're going to have is you're going to have these greater oscillations, okay, and then the same thing, and then they get smaller, and then same thing here, okay, something like that. So this is what it's seen here. Maybe not very well, but you can do it. You can see, and the period gets greater and